Morning, everyone. My name is Kellen. I'm a graduate student at UT Dallas working with Yves Kwan, and I'll be chairing this morning's session. It's my pleasure to introduce Erez Berg from the Weizmann Institute, who will be discussing strong correlations in twisted bilayer graphene.
Okay, thank you very much. Yeah, it's a pleasure to be here. I'd like to ask if you can ask questions during the talk. That would be great. Keep it more lively. Um, I'm gonna talk about strong correlations in twisted bilayer graphene. Yeah, please stop me at any moment if you need some more background. Yeah, these are my collaborators on this work. Johannes was a postdoc with me at Weizmann. He's now group leader at Max Planck Institute, Dresden. Yair is a student at Weizmann. Patrick was a student at Harvard, just moved as a postdoc to MIT, and these are the senior collaborators on this work. So just this is an outline. So the theme of this talk is going to be the tension that exists in this system, twisted bilayer graphene, between two types of descriptions, two limits, basically. So should we think about twisted bilayer graphene as a topological system? So we know that it has band topology, for instance. So should we think about the system as some kind of variant of the quantum Hall system or a churn system? Or since it has strong correlations, should we think about it as a doped Mott insulator? Okay, and both aspects of this physics exist definitely in the system, and it turns out that the system kind of solves this tension in a very interesting way. What I'd like to get to is some recent progress that has been made on the system and how to describe the intermediate temperature, a so-called flavor incoherent Mott semimetal regime that exists in the system. And there has been quite a bit of progress, both experimentally and theoretically, on understanding the properties of the system in this regime. Okay, so I suppose you all you all heard a little bit about twisted bilayer graphene. Okay, and what's special about the system is that you can realize very, very flat electronic bands. So how do we think about these flat bands? Okay, so there are sort of two ways we know how to get flat bands. The first one is just to put electrons in a very, very deep lattice, right? So this happens naturally in systems with D and F shells, for instance. So you just have electronic states that are very confined to the ions, and therefore hopping is very suppressed, and you get a very flat band. And you know that one of the characteristics of such systems, if the filling of every unit cell is odd, you would get a localized moment at every lattice site. The other natural way to get flat bands is just to put on a strong magnetic field on a 2D electron system. Okay, and then you know that you get Landau levels that are naturally very, very flat. But of course, the physics of these kind of flat bands is totally different from the physics of electrons in a very deep lattice. Okay, so these bands are actually topological. The electronic states cannot be completely localized. They have a strong overlap, and the system would have a quantized Hall response and so on. Okay, the question in this talk would be, well, there is this new way to realize a flat band in twisted bilayer graphene. Okay, so as you know, you place two sheets of graphene with a very specific twist angle between them, and under these conditions, you realize these extremely flat, even though not mathematically flat, electronic bands at the Fermi level. And how should you think about this? These flat bands? Should you think about them from the sort of more localized limit or from the topological limit, or are they somewhere in between? Okay, so it turns out that these bands do carry some special form of band topology. Okay, and this was realized quite early on in the study of this system. And for completeness, I'm just going to describe a little bit this type of band topology. I think it's interesting. So what's topological about the bands of twisted bilayer graphene? There is actually a very simple way to understand that. Okay, so here's again this picture of the band structure, and this is a zoom in into the narrow bands. Okay, so it's a pair of bands for every valley of graphene that are basically half filled when the system is charge neutral. So the Fermi level at charge neutrality is exactly between this pair of bands. Okay, they're extremely narrow. In the one particle model, the bandwidth of these bands is just a couple of millivolts. So here I zoomed in on these bands, and you see that this pair of bands actually touch each other at 2 points in the mini Brillouin zone. This is the Moiré Brillouin zone. And so there are Dirac points. These are two Dirac points. And of course, whenever you see a Dirac point, you have to ask what symmetry protects these Dirac points. Okay, so if you didn't have any symmetry, Dirac points or band touchings are not generic in 2 dimensions. So it turns out that it's the product of a 180-degree rotation and time reversal that protects these 2 band touchings. Okay, it's actually the same symmetry that protects the Dirac cones of monolayer graphene. This prevents the opening of a gap here. Okay, and in 2 dimensions, whenever you have a pair of bands and you have this pair of symmetries, you can actually define a winding number to each one of these Dirac points. So there's a chirality that you can define for each Dirac point. In graphene, you can think about the 2 Dirac points as right and left-handed, but in this kind of system, because both of these Dirac points actually come from the 2 layers, the 2 original layers of graphene, they actually both have the same chirality. Okay, so you can understand that from just starting from the 2 individual layers of graphene. Each one has its own Brillouin zone. Then you twist the 2 systems with a small angle relative to each other and hybridize the 2 because of tunneling between the 2 sheets. And both of these Dirac points actually originate from the same valley of the original graphene. Therefore, they actually have the same chirality. Therefore, okay, so it's two left hands. Okay, I'm a theorist, so it doesn't mean necessarily I have 2 left hands, but this is my image of that. Okay, so this means in particular that if you deform the lattice a little bit, okay, these 2 Dirac points might move around in the mini Brillouin zone, but they actually cannot annihilate each other. So you cannot separate these 2 bands, you cannot open a gap as long as the product of these 2 symmetries is preserved. Okay, so the fact that this band touching is protected, and actually there's no way to separate these two bands without breaking the symmetry. That means that there is some kind of symmetry-protected band topology characterizing this pair of low-energy bands. This is called fragile topology. Okay, so it turns out that it really is just a property of this pair of bands. It exists so long as the gap to the other bands remains open. But as long as that's the case, and we believe that is the case in the physical system, okay, so there are actually excellent experimental evidence for that. Then these 2 bands carry this kind of topology. Physically, what is the consequence of these 2 bands being topological? The consequence is that you cannot actually span this pair of bands at a given valley using exponentially localized Wannier functions that preserve the symmetry, that preserve these symmetries. Okay, so if you try to write some kind of real space basis, and that's a natural thing to do if you want to describe the effects of interactions in the system, then the wave functions would have power law tails. Okay, so they would be strongly overlapping, and that can change the physics in a fundamental way. Okay, so what does that mean? So this is sort of analogous to what would happen in a Landau level. It's the same story. Okay, a Landau level is topological. You cannot span a Landau level completely with a localized, with exponentially localized wave functions. And that has physical consequences on the interacting system. Okay, so what are the consequences of that? If you have two wave functions that have a strong overlap in real space, you want to put two electrons in these two wave functions, what you would expect is a strong exchange interaction between them. So the ground state, if you partially fill this state, might be a ferromagnet. Okay, so one thing that you expect, if this is the correct physics, is that in the interacting system, the system would tend to form some kind of generalized ferromagnet. Now, this system has not just the spin, it also has valley, and it has the orbital index of these two bands. So you'd expect some kind of generalized ferromagnetism in this spin and valley and orbital space. Okay, so some kind of generalized ferromagnet. There are many types of such ferromagnets that you can write down, and you expect some of them or all of them to be realized in different parts of the phase diagram. Okay, so that's one thing that you would expect. Each one of these generalized ferromagnets would have a different characteristic, different physical properties. Yes. Yeah. Yes, yeah. So yeah. Thanks for that question. Absolutely, indeed. So this chirality characterizes a single valley. Now, this band topology relies in particular on the fact that the two valleys are essentially decoupled at the single particle level. They're so far away in momentum space, okay, that it's very hard to couple between them. So to an excellent approximation, because of the small angle, they are decoupled, and that's why, yeah. So indeed, the other value would have the opposite chirality. Yeah, any other questions? So the simplest thing would be a fully, so suppose you half fill the system, you would expect a fully polarized ferromagnet. So in particular, for instance, if you fill one electron per unit cell, you would get just one mu Bohr from the spin. Now, there may or may not be an orbital moment as well. I thought it's mostly coming from the nesting, right? Because you're really flat. Yeah. So So it is a flat band. So you would say it's as nested as you can possibly get. But because it's flat, all the electrons are participating in the ferromagnet. So the simplest state that you would imagine is simply that the magnetic moment is just one per electron. Yeah. Make sure I understand this qualitative picture that have localized orbitals with lots of orbitals. Yes. Yes. It really is simple as I save Coulomb energy by having. Absolutely. That's it. Yeah, thanks. Okay, yeah, it's all Coulomb driven, of course. Yeah, it's a flat band, no kinetic energy. The only thing you need to minimize is Coulomb, and the way you do that is by putting all the electrons in the same spin or the same valley or the same flavor. You save Coulomb energy by doing that. Yes. Thanks. Okay, and this indeed happens in the system. We know that happens in various forms. So there are different experiments. Okay, so here's an experiment providing evidence for valley ferromagnetism. Okay, so the system at the filling factor of 1 away from charge neutrality. So you add 1 electron per moire unit cell away from half filling. The system tends to form this orbital ferromagnet. Okay, this is actually a real space image taken in Elizotov's group using a scanning squid. Okay, so you see these interesting magnetic domains. The length scale is a few hundreds of nanometers, which is a few tens of Moiré unit cells. And there are actually other forms of generalized ferromagnetism that are realized in this, this kind of system. The other type of ferromagnetism that has been detected a little bit more recently is a so-called inter-valley coherent order. Okay, so this is when spontaneously the system forms a coherent superposition of electrons between the two valleys. So if you think about the valley as a pseudospin, then this would be order in the plus or minus z direction, polarizing in the k or k prime valley, and this would be some kind of order in the plane. Okay, so yeah, both of these types of generalized ferromagnetic order are actually realized in this kind of system. So is this the end of the story? Should this just be thought of as some sort of complicated generalization of a quantum Hall ferromagnet? So it turns out that the answer is no. Okay, so there's more to the story. And at least for me, the first hint of that came from these experiments several years back about measuring the electronic entropy in these systems. Okay, so how do you measure the electron entropy in such a system? Okay, so in solids, as you know, you can measure specific heat and integrate that to get the entropy. Now, this is a two-dimensional system. It's a very dilute system. There's one electron for every 100 atoms, or actually 10,000 atoms, 100 squared atoms. So how do you measure entropy? So what these two groups did was actually to measure the electronic compressibility and to use thermodynamic relations to back out the entropy as a function of density and temperature. Okay, so these were experiments done in Shah-Khalilani's group and at the same time by Andrea Young's group. Okay, and before measuring the entropy, it was noticed that something is weird in the system. So here's a measurement of the resistance. So Dima Yefetov, I guess, was here yesterday. These are measurements from his group, but there were earlier experiments by other groups showing the same thing. So this is a map of the resistance as a function of the filling factor of the Moiré lattice and temperature. And you notice something a little bit odd that happens close to a filling factor of 1, for instance. So you see that at integer fillings, the resistance peaks. Okay, and it peaks very strongly at 2 and at -2, but there's also a much weaker peak at 1. Okay, so there's some sort of correlated state that forms whenever the filling of this Moiré lattice is integer. And this specific correlated state at filling factor of 1 has an interesting temperature evolution. Okay, so as you fill from charge neutrality, they label this state as a Fermi liquid. Okay, it looks more or less like a normal metal, shows quantum oscillations and so on. But then you see that there is this more weakly correlated metallic state and a more correlated state after you reach filling factor of 1. And as you heat the system up, that actually favors the more correlated state. Okay, so this is an indication that the correlated state actually has a higher entropy than the more weakly correlated state. And a direct measurement of the entropy actually confirmed this. So this is the electronic entropy from Shachal's group as a function of density at a different, this is at a fixed temperature of 10 Kelvin. This is for different in-plane magnetic fields. And you see that the entropy starts low, close to the charge neutrality point, but then it reaches quite high values. Okay, so blue here is zero in-plane magnetic field. Values of the order of 1 mu Bohr, or even a little bit more per unit cell. Okay, and moreover, this large excess entropy is, at least a big part of that is suppressed when you apply an in-plane magnetic field. Okay, so this is actually an indication of local moments. So what happens, especially close to integer fillings, but also in between, okay, is that at least part of the electrons get localized and contribute at this temperature of 10 Kelvin, contribute a large entropy coming from fluctuating spin or valley moments. Okay, at least the fact that a big chunk of this entropy is suppressed by an in-plane field indicates that at least a part of this entropy is spin entropy. Okay, so if there's some kind of valley orbital moment that would not be suppressed by an in-plane magnetic field, maybe by an out-of-plane magnetic field. Yes. Yeah, yeah. So, yeah, there's no quantitative understanding of this very well. Yeah. So I mean, most naively, you would expect a different. If you literally just think about one electron per unit cell or two electrons per unit cell in four orbitals, you would expect a different value. Yeah. Yes.
Can you give a sense of what scale that is relative?
Yeah. That's an excellent question. So yeah, so is this high or low temperature? What's the natural energy scale in this system? So the bands are supposed to be very, very flat. So the bandwidth is much lower than this. Not much lower, of the same order as this, the single particle band structure. But the Coulomb energy, if you just think about the Coulomb repulsion between two electrons, say, on neighboring Moiré unit cells, that's maybe 300 Kelvin. Okay, so relative to the microscopic energy scale, which is the Coulomb energy, this is actually quite low. Yeah. Yes. The y-axis is entropy per unit cell, yes. Yeah, so what's actually measured is compressibility. Okay, so the mu dn. So it's basically charging, basically how much do you need to change the chemical potential to charge the system, or by how much does the chemical potential change when you charge the system. And you use thermodynamic relations to get the entropy. So what you really measure is the derivative of the compressibility with respect to temperature. And that by a Maxwell relation, you can relate to a derivative of the entropy with respect to density. Okay, and you do some integrals. So yeah. Yes. Do you get a what? Do you? Yeah. So which do you expect to? Yeah. Yeah. So I mean, what has been seen before. And I may have a slide for that somewhere. So the compressibility actually does something very interesting as you go across this phase diagram. So in the same way that you see, at least at the final field, you see these peaks in the entropy at every integer. In the compressibility, what you see is actually very pronounced jumps. So the inverse compressibility has a kind of sawtooth form. It actually peaks each time you reach an integer and drops. Yeah, it is actually the other way around. It first drops, peaks after the integer and goes back down. Okay, something dramatic is happening in each one of these integers. The system really feels that. You expect that in a very strongly correlated system. The interesting thing here is that it comes with this very, very high entropy. So somehow these electrons, even though the bands are topological, these electrons are managing to localize. This was the sort of puzzle that was posed by these results. Yes. Yeah. So yeah. So it's a good question. Okay. Here. Yeah. So yeah. So I don't know that there's a direct measurement of that here. There's no time dependence of anything. there's no particular reason, why the system would fall out of equilibrium. This is not an extremely low temperature, so there's no problem of equilibration of the electrons with the environment. These are not particularly insulating states. When you have hysteresis, you see it, and there's a good reason for that. So, for instance, in these generalized ferromagnetic states, you see hysteresis right away. Okay. All right. So yeah. So the question is, how do these electrons manage to be localized and topological at the same time? And I think by now we have a fairly good understanding of how that happens. Okay. And the key to that is all in the nature of the electronic wave functions of these flat bands. Okay. So what was noticed early on is that the wave functions of the flat bands are not uniform across the Moiré unit cell. In fact, they're very, very strongly peaked in the so-called AA regions of the unit cell. Okay, so what is the AA region? So you have the two layers of graphene that are twisted with respect to each other. And that means that if you look at the registry of the two layers across the unit cell, that actually changes in real space. Okay, so there's some region in the unit cell where the A sublattice of one layer is aligned with the A sublattice of the other layer, and then you move to a different part of the unit cell, and the A sublattice is right above the B sublattice, and so on. Okay, so you can label different parts of the unit cell according to the local registry, and it turns out that the electronic wave functions of these flat bands are very strongly peaked in the AA parts of this unit cell. Okay, so this sort of invites you to think that maybe you can form some kind of localized basis that lives mostly close to the AA parts of the unit cell. Now, of course, these are topological bands, so you could not possibly span the entire band this way, but maybe you can span most of the band. And this intuition was formalized nicely by this paper of Song and Bernavig. Okay, so it turns out that you can choose a basis in which almost the entire flat band is actually spanned by localized, actually Gaussian wave functions that are localized close to the AA orbitals. Okay, and these localized one-year orbitals span almost the entirety of this pair of flat bands. So there are two such orbitals per unit cell, with the exception of the vicinity of the gamma point of the Moiré-Brillouin zone, where the actual wave functions of the flat bands are actually orthogonal to these wave functions. And there's actually a symmetry reason for that. Okay, so the symmetry of the states close to the gamma point don't match with the symmetry of these localized one-year orbitals. So what they proposed is actually to use a basis where which spans not only the flat bands but also the two pairs of neighboring remote bands, such that here's what the basis actually looks like. Okay, so there's a pair of completely flat and trivial bands, and these four Dirac-like bands, and they hybridize to form the actual correct band structure. Okay, but most of the flat bands can actually be described in terms of these localized one-year orbits. Okay, and then it's clear that what Coulomb interactions would tend to do is to localize electrons on these localized one-year orbits. Okay, and since they form almost the entirety of these flat bands, you would get this localized Mott-like behavior. Okay, so so far this is literally just a change of basis, but it's a very useful change of basis that sort of gives you a guide how to treat correlation effects in this system. Okay, so of course we want to solve the problem. We want to see what are the properties of interacting electrons in these flat bands, and we don't have a lot of techniques how to do that. Our technique of choice was quantum Monte Carlo. Okay, so we're interested in this regime of intermediate temperatures, when the temperature is much lower than the Coulomb scale, but still higher than any ordering scale, any temperature where there is some sort of generalized ferromagnetism. And what we've done at the charge neutrality points, so at nu equals 0, namely 4 electrons per unit cell, okay, so half of the 8 states, 2 valleys, 2 spins, 2 orbits are filled. At this point, because of the approximate particle symmetry of the problem, there's actually no sign problem for a quantum Monte Carlo. So we can literally just solve the interacting problem on a fairly large system, and that's what we've done. Okay, so let me just define what the problem exactly is. So we treat this pair of flat bands per valley per spin, project out all the other bands. We have long-range Coulomb interactions. Okay, no further assumptions, basically. We can just find the thermodynamic properties of the strongly interacting system. And the reason we can do that is because we're at charge neutrality. Okay, this is a very special point because of particle hole symmetry. Okay, and this is what the entropy looks like as a function of temperature. These are different system sizes, just to see the systematics of what happens when we increase the system size. Okay, so at low temperature, the system forms some kind of generalized ferromagnet. It breaks spin and valley symmetry in some particular way, and the entropy is low. Okay, and when you reach a temperature of around 10 Kelvin, the entropy jumps. This is melting of this type of order. And then there's notice that this is a log scale. Then there's an intermediate temperature window, maybe between 15 and 50 Kelvin, where there is this knee in the entropy, this kind of quasi-plateau. And then ultimately the entropy keeps going up. The value of the entropy here is this log of 8 choose 4. This is just the entropy you would expect if at every site you have basically a Hubbard model. It's basically like a Hubbard site. There's a big charging energy that forces the charge on that site not to fluctuate. So there are exactly 4 out of 8 states being filled. But otherwise, the flavor, spin, valley, and orbit are completely random. Okay, so they're fluctuating. This is basically fluctuating moments that you get out of this system. Yeah.
Previous picture
Yeah.
said in most of the band, you
Yes.
can fill buffers this part touching.
Yes.
Where the states are not localized.
Yes.
And it looks like your MC charge are maybe a little bit above that line.
Yeah.
And I would have expected it to be somehow a little bit below.
Yeah. Yeah. So right. So first of all, indeed, I believe that what happens here is that there are a little bit of also the charge is also fluctuating, so that also gives you a little bit of extra entropy. Yeah. In fact, the black line here is just the entropy you would get from a single site. Now that is a little bit below, so that this means that what I said doesn't quite explain this fact. But yeah, it's a good question. Yeah, it's close to that. We have some error bars. Okay, yeah, but the black line here is simply the entropy you would get from a single Hubbard site with 8 states overall and 4 electrons. Okay, so you see this plateau at this value at low temperature, and then ultimately at some temperature the charge starts to fluctuate. You get and the entropy increases. Okay, so what are the characteristics of this intermediate state? So okay, we can look at the electronic spectral function in this calculation. Okay, so you do that by analytic continuation of the data. The quantity that's actually calculated is in imaginary time, so you have to analytically continue, but you can do that. So this is what the spectral function looks like somewhere within this plateau of the entropy. So it's the spectral function as a function of a momentum across the mini-Brillouin zone, and it has this interesting characteristic. Okay, so over most of the Brillouin zone, you just see 2 electronic bands at some energy, okay, plus or minus 20 millivolts. This is basically the Coulomb scale. So this looks like Mott bands. Okay, if you just have a Hubbard model and you fill it and you ask what's the energy to add one electron, it's U. It's the local Hubbard interaction. What's the energy to remove one electron? It's just minus U. Okay, and these bands for a Hubbard model in the strongly interacting limit would just be completely flat. Now, this is the case almost everywhere across the Brillouin zone, with the exception of the vicinity of the gamma points, where this gap, this Mott-like gap, actually closes. So this is an interesting state. It looks like some sort of hybrid between a Mott-Hubbard kind of insulator and a semi-metal. And as you lower the temperature, so this is the spectral function over here, as you lower the temperature further, you actually open a gap also at the gamma point. And we understand how that happens. This is a particular symmetry Bokin state called the KIVC. This is a variant of this state that has a coherence between the two valleys. Yeah, the red here is what would be the single particle bands. Yes, yeah. So you see that they're actually very, very narrow, right? So this scale really has nothing to do with a single particle dispersion. Yes.
Okay. But get a conductivity and see once the gap is closed, is there any sign of linear?
Yeah, we haven't done that. Yeah, we will do that. I think we have a better way now that doesn't involve this analytic continuation. Yeah. Yeah. This model is band projected. Yes. Yeah. Okay. Any other questions? Okay. So yeah. This type of dispersion in the intermediate temperature regime, where you have a Mott-like bands over most of the Brillouin zone, but a semi-metal close to the gamma point, this was actually observed by other people using other methods. Okay, so in particular using DMFT, dynamical mean field theory, people saw this very similar behavior. Okay, different groups. So these very flat Mott-like bands over most of the Brillouin zone and a gap closing close to the gamma point. Okay, so this calculation is DMFT actually using the heavy fermion basis. And most recently, there has been an analytical method that I'm going to expand on, describing the system that actually captures this behavior. Okay, so Mott-like bands basically at plus minus U, the local Hubbard interaction, and a semi-metal like gap closing close to the gamma point. Okay, so this is an analytical method developed by Patrick Ledwith and friends, and it also by Bernevig using the heavy fermion basis. I'm going to talk more about this. The interesting thing about these calculations is that that really caught my attention. Okay, so the width here, okay, the width of these bands is actually completely artificial. This is just a broadening in order for us to see the spectral lines. What you really get out of these calculations are delta function like bands. Okay, so even though this is a very strongly interacting system, you get infinitely long-lived states, which is very weird, very surprising to me. This motivated us to actually look a little bit deeper into this calculation. Okay, what they've actually done, that I'll describe in the next slide, is they identified a small parameter you can use in the system in order to control the calculations, in order to actually make analytical progress, which is really impressive. Okay, so we actually wanted to understand this a little bit better. And let me just spend a few slides about theory and what the recent developments are. Okay, so we want to calculate properties of this system. Okay, and we want to use this topological heavy fermion basis. Okay, so here's the Hamiltonian that we want to solve, or the action. These are the so-called C fermions. These are the fermions forming a Dirac-like dispersion. These are the more dispersive electrons. And these are the F electrons forming this pair for each valley, each spin, this pair of very flat bands. These are very localized orbitals, and they are hybridized in some particular way. There's a interaction. For simplicity, the only interaction that we keep in this model is the biggest interaction, basically the local U acting on the more localized F-like electrons. Now, of course, the notation here, C and F electrons, comes from the analogy to the heavy fermion systems, where you describe the system in terms of the coexistence of more localized F orbitals and more dispersive C electrons. Okay, and now we want to make progress on this problem. As you all know, this is a Kondo lattice. This is a particular Kondo lattice type Hamiltonian, and that's in general, that's a very difficult problem. The effects of strong correlations, of course, here are very, very important. So what do we do? How do we make progress? So we can't use our U as a small parameter, of course, because the effects of U are very non-perturbative. We also don't want to use the hybridization as our small parameter. So luckily, it turns out that in this particular problem, there's a different small parameter, which is neither of these, that can actually be used in order to make analytical progress. And this is really a special property of twisted bilayer graphene, and it's related to this fact that over almost the entire Brillouin zone, the flat bands have this localized character, and the hybridization really acts. The hybridization is very strong, but it only acts in a very small part of the Brillouin zone. Okay, so what we're going to use is a small parameter, which you can think about in this way. Gamma is the strength of the hybridization at the gamma point. Okay, and V star is the bare speed of the C electrons. That's actually very high. That's actually of the same order as the bare Dirac velocity in graphene. And GM is the size of the more Brillouin zone. Okay, so this is going to be our small parameter. In real life, it's not that small. This parameter called S squared. This is maybe between 1 over 10 and 1 over 20. Okay, so that's how small our small parameter is. But that's what we have, so we try to do our best. Okay, now here's what it looks like pictorially. This is what the dispersion of the topological heavy fermion model looks like before hybridization. So you get this pair of very flat bands coexisting with very dispersive Dirac electrons. This is the hybridization strength, okay, maybe 50 millivolts, and this is the speed of the bare speed of the C electrons. And really what this parameter is describing is the fraction of the Moiré-Brillouin zone where the C and F electrons are strongly hybridized. Okay? Yes. Yeah. Sorry? So in this model there is. It's not essential. In the real system there isn't. Okay, we know that the terms that break that, you can add that to this description and it doesn't change anything qualitative. Okay? So yeah, so that's our small parameter that we want to use in order to do the calculations. And this is actually the small parameter identified by Patrick and friends, and used in order to get the spectral functions that I showed in the last slide. Okay, so how do we use this small parameter in order to do calculations? Okay, so there is actually a systematic way to do that, and this is what we've been developing. Okay, so the idea goes back to these old works. Okay, so what you can do is formally treat the system, formally do a hybridization expansion to all orders. Okay, so you do that by basically by tracing out the F electrons with respect to a zero hybridization action. And what you obtain by doing that is a C electron only action, okay, that has vertices. Okay, this is dying on me. Maybe I'll use this. Yeah. So this is a C electron only action that has these complicated many-body interactions. Okay, so basically n-body vertices of the C electrons, and each of these vertices, capital gamma, is just a local correlator of the F electrons with respect to an action, which is just a single site Hubbard action. Okay, so you can represent this pictorially as follows. So the gamma 2 is just a one-body term of the C electrons. It's frequency dependent. Okay, these vertices, because we've traced out the F electrons, would be non-local in time, so they're frequency dependent. This is just the on-site correlator, one-body correlator of the F electrons, and that comes in as a one-body vertex for the C electrons. And then there's a two-body and three-body vertex and so on. Each one of these vertices is just a local correlation function of the F of the F sites. Okay, so this is a very complicated looking action, of course. It's exact so far. And the question is, how do we make progress on that problem? Okay, and it turns out if we try to calculate any physical quantity, for instance, the self-energy of the C electron, okay, so the first term is easy because this term is Gaussian. It's a quadratic term in terms of the C electrons, but then we have these loop corrections to the self-energy. We can connect these n-body vertices in many, many ways. And here a small parameter comes to our aid. Okay, so it turns out if you compute the first few terms of the series, it becomes apparent very fast that each one of these loops in these diagrams actually comes with a suppression factor, which is basically that S squared. Okay, so the argument is really a phase-space argument. The momentum integrals over these loops sum over the entire Brillouin zone, but the contribution is only coming from the region where the F and C electrons are actually strongly hybridized. So you get this factor, which is the phase space of hybridization between C and F for each loop. Okay, so each one of these higher loops diagrams would be suppressed by a factor of S squared to the power of the number of loops. Okay, so if you analytically continue this self-energy to real frequency, it turns out that this one loop term in the self-energy actually diverges. So you have to be a little bit careful. You have to resum a particular series, basically an infinite series of diagrams to all orders of S squared, but it's only a subset of diagrams. And we can actually do that in the limit where the number of flavors of F electrons is large. Okay, in reality, this NF is equal to 8. But we've done that. Okay, I won't get into details. Let me just flash out some results. Okay, so first of all, to order S to the power 0, this is the lowest order in this expansion. What you get is you basically reproduce these results by Ledwith et al. And by Hu et al. Okay, so this is the so-called Hubbard 1 approximation. So the Hubbard 1 approximation, where you keep only this quadratic term in the C action, okay, there's a self-energy, which is simply the localized F Green's function. Okay, so this is the exact answer to the power to order S to the power 0, and you already get this this qualitative feature that you get Mott-like flat bands. Now this died. Get back to this. Yeah, now this works. Okay, so you get these very flat Mott-Hubbard-like bands over the entire Brillouin zone, and a band touching close to the gamma point. But these bands are actually mathematically narrow. Okay, so the width of the line widths here is exactly 0. That's remedied once you go to higher loop order. Okay, so this is sort of this resummation that I've shown before. And it turns out that then these Mott bands actually broaden quite significantly. Okay, so the width of these Mott bands is actually S squared, our small parameter, times U, which when the hybridization is large is the only energy scale of the problem, times the number of F flavors, which is 8. Okay, and they're very broad everywhere in the Brillouin zone, and you get this semi-metallic dispersion where the lines are actually very narrow. Okay, they're not infinitely narrow. These Dirac-like electrons actually scatter off the moments formed by the F electrons, so they still have a finite lifetime, but they're much more narrow than the Mott bands. Okay, and in principle, using this technique, we can calculate any property that we want. For instance, we can calculate the flavor spin and valley susceptibility of these of the system. And as you might expect, it has a Curie-Weiss type behavior coming from these nearly localized F moments. Okay, and we can also calculate the Weiss temperature and its scales in this way. Okay, so of course this type of description doesn't hold all the way down to the lowest temperatures. It has to break down. It would break down at this Weiss temperature where the moments actually order. Okay, so yeah, and this calculation is not confined only to charge neutrality. This is what happens as you move away from charge neutrality. Okay, so far we've done the calculation only at integer fillings. And it has this interesting feature that is also seen in the DMFT calculations. Okay, so as you move to non-zero fillings, you still get these two Mott-like bands, but they're very asymmetric, both in terms of their weight, of course. Okay, so that just reflects the filling, but also their width is extremely asymmetric. Okay, so as you fill the system, the upper Hubbard band becomes very blurred, and the lower Hubbard band remains sharp. Okay, and this feature is definitely seen also in DMFT, and if you squint a little bit, it's also seen in experiments that I'll show next. Yeah. Yeah. So this is an intermediate temperature calculation, right? So we know it has to break down at some point, and the way this calculation breaks down is that it's an expansion in this small parameter S, and we see that some terms in this expansion diverge at low temperature. Okay, so one type of divergence that we get is just coming from the flavor susceptibility, but there's also a Kondo-like divergence. Okay, and it's a competition between these two. And of course, then it's challenging, as usual in the Kondo lattice type problem, it's challenging to take these two things on equal footing. Okay, now one thing I can say, okay, in this type of limit, in the small s limit, just like in the Doniak argument, right? So the Weiss temperature is parametrically larger than the Kondo temperature, because the Kondo temperature would be exponential in this parameter s squared. Okay, so if the system is literally deep in the limit where we know how to do the calculation, we know that it would order way before any Kondo physics starts to kick in. Okay. All right. Yeah, in the remaining few minutes, yeah. So I'll talk a little bit just about experiments. So very recently in Shahar-Lilani's group, the spectrum of electrons in twisted bilayer graphene has actually been measured. And I want to describe that. So the way they measure that is using this wonderful new technique developed by Shahar's group, which is the quantum twisting microscope. Okay, so how do you measure electron dispersion in solids? So the method of choice would be ARPES, but it turns out that ARPES doesn't have the momentum resolution needed to resolve these very tiny Moiré Brillouin zones. And Shahar devised a different way to do that. Okay, the way you do it is this is your system. This would be twisted bilayer graphene, and this is a tip. The tip is basically monolayer graphene. Okay, so there's a flat part on this tip, which is simply monolayer graphene, and you can bring these two into contact. This is basically an AFM tip, so you can bring these two into contact, and measure the current between one and the other, basically tunneling of electrons from the tip to the system. And moreover, you could also rotate the two relative to each other. So basically this sample holder can rotate. Okay, and what this means, if you think about tunneling from one to the other, okay, so the tunneling is momentum resolved because this contact region is flat and big enough. Okay, and as you rotate, the Dirac point of the tip basically traces this arc in the mini-Brillouin zone. Okay, so the angle of rotation translates into momentum resolution, and by the bias voltage, you also control the energy. So you get basically the spectral function of the sample as a function of momentum across this cut in the mini-Brillouin zone and as a function of energy. So this is really a way to directly image these the bands of the sample. Okay, which is perfectly suited to this type of system. Okay, and here I'll just flash a few results. So they've done the experiment first for a twist angle of 1.2 degrees away from the magic angle, and this is what it looks like. So this is a cut through the mini-Brillouin zone, and you see very clearly this band crossing close to the K point. This is basically the Bissinger-McDonald type dispersion. Okay, so these are the mini bands that are narrow but not extremely narrow. Okay, a few tens or 100 millivolts, and you very clearly see this Dirac point of the Moiré bands. But as you approach the magic angle, this dispersion completely changes, and it actually has exactly the character that I've shown before. There are these two very flat bands at plus minus 20 millivolts that are almost non-dispersive everywhere in the mini-Brillouin zone, with the exception of the gamma point, where this gap actually closes. So this is the so-called, believe this might be the so-called Mott semimetal, the sort of hybrid behavior that should remind you of this picture. Now, let me just close with one caveat. Okay, so this is one very natural way to get this dispersion, and that made everybody happy. But there's another way. Okay, so this is again this dispersion from the quantum Monte Carlo calculation. This is for a perfectly symmetric system, no strain. But it turns out that if you just introduce a little bit of heterostrain, so relative strain between the top and the bottom graphene layer, you get a totally different state that has a very similar dispersion. So also flat Mott-like bands over the entire, almost the entire Brillouin zone, with the exception of a band touching close to gamma. And we still don't know in the experiment which of these two is actually realized. We're starting to believe that maybe it's more likely to be this one. But that's still open. How do you actually distinguish these two directly from a single experiment? Okay, yeah, so let me just finish there. Yeah, thank you very much.
Do we have any quick questions? Any other quick questions? No? All right, let's think.